This is lesson 5 of Basic Algebra in full series, and you are going to learn everything about powers from the absolute beginning till the very much advanced level. So let's begin. Welcome back to Math in Full, where mathematics is connected. As promised, this lesson is on powers or exponents or indices, which is a faster, more efficient and easier way to simplify the multiplication family. At the end of this lesson, you will learn everything about powers, especially the laws of indices or the laws of exponents. Just to make sure that everything is very clear, especially for those of us who are returning to math after a long time or who are doing mathematics for the first time, we are going to do a recap or a refresher. So if we had 3 times 3, this is 9. But another way you could write this, just like we mentioned in the last lesson, is 3 raised to power 2. What does this mean? It means that this 2 here as a superscript is telling us that this 3, which is called the base, is multiplying itself 2 times. This 2 indicates the power or index. The plural of index is indices or exponents. So these are the terms that these 2 symbolizes or represents. So it's just a way to tell us that the base is multiplying itself a particular number of times, which is represented by that superscript that is called the index or the exponent. The reason for powers is simple, just to reduce the burden of writing numbers repeatedly. Imagine if this wasn't 3 raised to power 2, if it was 3 raised to power 100, you now have to start writing 3 times 3 times 300 times, which actually wouldn't make sense. There won't be enough space to contain it. So that is the importance of powers. Now look at this again. If we had 2 times 2 times 2, the answer to this is 8. But if we wanted to represent it in index form or in powers or in exponents, we will say 2 raised to power 3. Again, the 3 here is the exponent or the index. The 2 is the base. So this is the idea of powers. Now that we have understood that, let us now talk about the popular powers. What do we mean by the popular powers? From what we've written, we can have the superscript 2, we can have the superscript 3, 4, and so on. Now, the popular powers are the superscript 2 and 3 because they are the ones that occur more frequently in mathematics. That's why I call them popular. So because they are popular, they are now given a special name. So the superscript of 2 is called square, while the superscript of 3 is called cube. So what I'm saying in essence is, instead of you saying 2 to the power of 2 or 2 to the power of 3, because that's how it is pronounced when you use powers, you can just say 2 squared or 2 cubed. In the same way, you can say 3 squared, 5 cubed, and so on. So what we are saying is squared is the same thing as raised to the power of 2, and cubed is the same thing as raised to the power of 3. Now, we've agreed that 3 times 3 is equal to 3 to the power of 2, which is equal to 9. Now, what if we take off this 1, and then we want to find what is that number to a particular power that gives us 9? When you want to go this way, that is the reverse. It is called roots. So, we say, what is the root of 9? Now, just like the index or exponents, the roots will also have different levels, just like we have raised to power 2, raised to power 3, 4, and so on. So for the roots, we will have the second roots, the third roots, the fourth roots, and so on. You will now wonder, why didn't I say the first root? Because just as in indices, there is no first power. Why? Because the whole idea of powers is a number multiplying itself. So for a number to multiply itself, it means that that number must have at least 2 copies involved. So there can be just first power. So in the same way, there is no first root. So the root starts from the second. Now, just as in powers, we also have popular roots, and I'm sure you already know what the popular roots will be. Since the power of 2 and the power of 3 are the popular powers, also the second root and the third root will be the popular roots. So because they are the popular roots, they also have special names. So the second root is called the square root, and the third root is called the cube root. So how do we represent this root, since we've seen how to represent power? To represent roots, you use this sign here. Now, since this sign is the root sign, how does it distinguish one root from another? That is, how does it tell us this is the second root, third root, fourth root, and so on? Now, because the second root, which is the square root, is the most popular root, this sign is reserved for it. So once you draw this sign and put a number here, which is to the right of it, inside the space there, then this automatically means square root. So in this example, this is square root of 9. Okay, if you now want to represent any other roots, you have to put that same superscript you put in the powers. You have to now put it in this small arc here. So if you put 3 here, it tells us this is cube roots. If you put 4 instead, it tells us this is fourth root. If you put 5, it tells us fifth root, and so on. So this is how the roots sign is represented and how it tells us which particular roots we are talking about. If there is no number in this groove here, then it is square root. Now, let us quickly mention here that when you are writing the number, that is the subscript, in this case it will not be subscript because the number is very small and it is below, unlike in powers where it was above. When you are writing it, you have to make sure that the number is extremely small and is written inside the groove like this. If you don't do it that way, then you may confuse it with, let's say, 3 root 9, which is a totally different thing. In mathematics, when a whole number multiplies a root, you can remove the multiplication sign. So instead of saying 3 times root 9, you can simply say 3 root 9 and it's accepted. So if you are not careful, and you don't write that subscript properly in the groove, cube root of 9 or whatever it is you are trying to say the cube root of may now look like 3 root 9, or fourth root of something may look like 4 roots whatever. So that's why you need to be very, very careful. The subscript you are putting must be in that groove and must be very, very tiny. Now let us also say here that a root is equal to 1 over whatever power it is. What do we mean? We mean that if you had, as we gave in the first example when we started, 3 raised to power 2 is equal to 9. And from what we've said now, the square root of 9 is 3. So what I'm trying to say here now is, instead of saying square root of 9 is 3, you can say 9 raised to power half is 3. Or 9 raised to power 1 over 2 is 3. So what we are saying is that roots is the inverse of powers. Of course, that's what we've described since this lesson started. But I'm now going on to say that mathematically it is also so. So in the same way, the other example we used, 2 raised to power 3 is 8. Or we can say 8 raised to power 1 over 3 is 2. Because the cube root of 8 is 2. Let us now talk about the properties or the characteristics of roots and how you can use this to your advantage when you want to simplify them. The first thing we will talk about here is that if we had 2 times root 3, for instance, we can go ahead to say that this is 2 root 3. We remove the multiplication sign. Why are we doing this? We are doing this because roots and powers belong to the multiplication family, just like we said in lesson 2. In that lesson, we called them cousins of the multiplication family. But you can just say they are members of the multiplication family. Because as we've seen since this lesson started, you understand that roots and powers were created from multiplication. So that's the reason why we can do this manipulation, 2 times root 3, and remove the multiplication sign. And it gives us 2 root 3. Now, if we had this same thing, but 2 plus root 3, you can't go any further here. You cannot say 2 root 3. No, it ends this way, 2 plus root 3. Because Plus is not a member of the same family where roots came from. Plus is part of the addition family. So this is one of the major properties of roots you must know, because this is one of the mistakes people make. When they see plus, they still manipulate it with roots. You cannot manipulate plus and minus with roots. There is indeed one situation in mathematics where roots can interact with the addition family, and that interaction is not really a real interaction. You understand why I'm saying this? Let's look at this example so we can explain it better. If we had 2 root 2 plus 3 root 2. Now, if you notice from this expression, each of these terms have something in common. And what is that? Root 2. So, if we assume that this root 2 is a variable, let's even replace it with, say, x. So that means this is like 2x plus 3x. And now from our lesson 3, we know that 2x plus 3x is 5x. So in the same way, 2 root 2 plus 3 root 2 is 5 root 2. That's it, if we replace the x with root 2. So this is telling us that in mathematics, roots act as variables. Roots are looked at as variables. And based on that, just the same way you can add like terms. Of course, you know that a term is like or unlike based on the variable it contains. We've already done that in the first lesson. So you can add like terms, that is terms that have the same variables. In the same way, you can add like roots. So because these two mixed roots have the same roots, they now become like roots, and so you can add their coefficients just like you can add the coefficients of like terms that have the same variable. So you now see the reason why I said this is not even a real interaction, because the root itself doesn't change. As you can see in the answer, it still remains root 2. The only thing that changes is the coefficients. You are combining the coefficients just because the two roots are alike. So that's why I said the interaction is not even a real interaction. So you see, the concept of multiplication family and addition family still remains intact. Nothing changes, because this root is just an object of a conversation that has to do with the coefficients of the roots. Now, let me quickly now add here again that just like you cannot add y and x, you cannot add unlike roots. So if this was 2 root 2 plus say 2 root 3, you can't add it anymore. This is how it will end, because the two roots are unlike, so you cannot add them. So you see what I mean by it is not a real interaction. You can only add roots that are like. Again, just like we mentioned in lesson 2, when you have a combination of terms that have roots and the operators there are from different families, you cannot manipulate them. You must use order of operations or BODMAS or PEMDAS. It also applies to roots. So if you had 2 root 2 plus 2 root 3 times 3 root 5 divided by 4 root 6 or whatever it is, you can't do any manipulation or move them around. You have to use order of operation. So what I'm basically saying is that everything we know in mathematics, everything we've learned from lesson 1 up to this point remains the same. Nothing changes, including this one I just mentioned, that you can add like roots. Is still in line with what we've mentioned. The only reason why it is looking a bit different is because I've already said that roots are part of the multiplication family, and yet this particular thing seems to be combining it with the addition family. Please do not mix it up. Now, another thing you must know is that the inner part of a root, when I say inner part, I mean this part that contains the term or the number that it's bearing the root sign. This inner part of the root is sacred. Just take it as it is sacred. It is very, very difficult for anything to get into that root space there. In fact, there are only 2 ways something from outside can enter that sacred space of the root. The first way is if that thing coming in is a root itself. So what we are saying here is that if we had root 2 times root 5, we can go on to say that this is equal to root 2 times 5. As you can see, they've unified their roots and the two numbers have come together inside that sacred space of the roots. This is what I mean by being a root yourself. So this goes on to give us root 10. So this is the first way something can get into the sacred space of a root. Now, the second way is an option for those things that are not roots. So if you are not a root, you can still come in, provided you are willing to do one thing. What is that thing? You must raise yourself to the power the root is inverse of. What do we mean? Let's look at this example. Now, if we had 2 times root 5, now from this one, you see that this 2 doesn't have a root, and it cannot go into this sacred space where 5 is. So what you have to do, or what 2 has to do to get into this sacred space, is it has to square itself. So this is equal to the square root of 2 squared times 5. Now what we have done here is that we have made sure that we squared the 2 first before bringing it into the root sacred space, so that by the time we find the square root, it brings the 2 out back the way it was. So what we've done, basically, we've not really changed anything. We've left it exactly the same way it was, but we've put it in a position where it can be simplified. That's the whole idea of squaring it before bringing it in. So these are the 2 ways something can go into a root sign. Unfortunately, these 2 ways are one for one that has a root and one that doesn't have a root. But notice something in these 2 examples. In both cases, we are dealing with the multiplication family. Look at here. Root 2 times root 5. It is times. Here as well, we have 2 times root 5. None of them have plus or minus. So that still goes on to reinforce what we've been saying since this series started. The multiplication family is different from the addition family. You can manipulate things in the multiplication family when the multiplication members are there. You can manipulate things in the addition family when only the addition family are there. Once the 2 things cross, once the 2 operator families cross in an expression or an equation, you cannot manipulate them. Now let's look at examples to prove what we are saying. Now we are still going to use the same example. So if we add root 2 plus root 5, nothing can happen anymore here because this is plus we are dealing with. So even if 2 has a root and 5 has a root, they cannot breach each other's sacred space simply because the operator here is a foreigner, is not a member of their family. Now, even the second example, if it was 2 plus root 5, again, nothing can happen here anymore. Even if 2 wants to square itself, it cannot square itself and go into the sacred space of 5 because the plus here is a foreigner, is preventing it from doing that. So you always need to remember that there are 2 families in mathematics. This is like the basis for everything you do. Once the operators are from different families, you cannot manipulate things the way you like. I'm going to reiterate it again for those who are wondering or who are still unclear. Root 2 plus root 5 is not root 7. This is wrong because they cannot breach each other's sacred space because of the plus sign. Again, root 2 plus root 5 is not the same thing as root 2 plus 5. This is wrong. Also, 2 plus root 5 is not equal to 2 root 5. This is wrong. Why? Because the plus is not a member of the family, is a foreigner. So it's going to cause a problem. So this is wrong. If we add root 2a plus 5 times root 5 minus y, this is still the same thing as root 2a plus 5 multiplying 5 minus y. So we still can unify the roots and keep the terms the way they are, multiplying themselves in their sacred space because the 2 roots were multiplying themselves in the first place here. But if this was plus, then we cannot do this. So it doesn't matter if what is in the roots is a complicated expression. As long as we can take it as one unit and it is multiplying another root, then we can still multiply those 2 terms in the 2 roots as a unit in one root. In the same way, just like the second case of how a number can get into the sacred space of a root, if we had it this way, 2a plus 5 root 5 minus y, same thing. If you can square 2a plus 5 as a unit, then you can bring it into the sacred space of this 5 minus y. So it gives you root 2a plus 5 all squared multiplying 5 minus y. So this is just the same thing I've talked about, just to say that it also applies even if the expression looks complicated like this. Now, unless you are able to remove the root sign, you cannot do any manipulation with the outside world. That is, a root cannot interact or mingle with the outside world unless that root sign is removed. Apart from these situations we've talked about earlier, where something from the outside can interact with something inside the root, if those conditions are not met, then a root will have to find a way to simplify itself and remove the root sign before it can interact with things on the outside. Why is this so? It is so because that root sign is just a camouflage. The root sign is telling you that whatever number or term that is inside it is a camouflage. It is not the actual value of what it is. For instance, if we had root 4, you cannot manipulate that 4 with something on the outside. Say you want to multiply it by 2, and then you go ahead and say this is the same thing as 4 times 2. That gives you root 8. No, this would be wrong because 4 is not actually 4. Once it steps out of the roots, it becomes 2. Okay, once it becomes 2, then 2 times 2 gives you 4. So you see that you are now mathematically wrong. This is the reason why I said the inner space of a root is sacred. So what we are saying in essence is that 5 times root 2 is not equal to root 10. No, it is also not equal to 10. This is also wrong. Again, root 4 divided by 2. You cannot say 2 divided by 2, 1, then 2 into 4, 2. The answer now gives you root 2. This is absolutely wrong because you cannot breach the inner part of the root to cancel out, in as much as it's still the division family. But this number is not a root, so you cannot cancel out that way. It is only if you had root 4 over root 2, then you can unify the roots like we talked about when we started this section. You can unify it to give you root 4 over 2 because this root 2 meets the requirements to go into that sacred space of 4. And what is the requirement? First requirement is that it is a root itself. The second requirement is that this is the setting of the multiplication family because division is part of the multiplication family. So you can unify the roots, then you can now cancel out 2 here 1, 2 here 2. It now gives you root 2 as the answer. But in this case where we have root 4 over 2, you cannot do that because this 2 does not meet that requirement. Now, another thing to note about roots is that just like you can split numbers into their prime factors, you can also split terms inside their roots. This process is what we call prime factorization. To understand this, we have to go back a bit to something that is more basic than even what we are talking about. Now, 10 divided by 2 gives you 5. There is no remainder. Now, because 2 can divide 10 without any remainder, then 2 is called a factor of 10. And in the same way, 10 is called a multiple of 2. So what we are saying is that the factor of any number is that number that can divide the number we are talking about without having any remainder. While the multiples of a number is the times table of that number. So 2 times 1, 2, 2 times 2, 4, 2 times 3, 6, and so on. All those numbers you get from the times table are all multiples of the number. Now, there are some numbers that have no other factor except themselves and 1. Such numbers are called prime numbers. In other words, a prime number is a number that is greater than 1 and can only be divided by itself and 1 without remainder. The most popular prime numbers we know are 2, 3, 5, 7. Now, if you look at these numbers, there is no other number that can divide them without giving you a remainder. 2 cannot divide 3 without giving you a remainder. There is no other number that can divide them. So these are prime numbers. So what do we mean by prime factorization? Prime factorization means when you get the factors of a number and all those factors consist of just prime numbers. So in this case, we use the smallest ones we know, 2, 3, 5, 7. So let's even start with the example we've written. Now, if we wanted to write 10 using prime factorization, we can split 10 to be 2 times 5. So that is prime factorization when we are looking at 10. It gives us 2 times 5. However, in most cases in mathematics, you may not have that time to start thinking of what exactly are the prime factors that will give us that number. You can start with any number you can remember and then work your way through. What do I mean? Now, let's look at this as an example. If we have root 72, we want to solve it, but we don't know the square root of 72. So what do? We find the prime factors of 72. Now, we don't know the prime factors of 72 by heart, but what we do know is that 72 is 9 times 8. So we first of all split it to 9 times 8. This is acceptable everywhere all over the world. You have to split it to what you know and then keep on splitting until you get to what you need. So when we get to this point, we can decide to say we know the square root of 9 and pull this 9 out as 3 because square root of 9 is 3. So this now gives us 3 root 8. Then we can go on and continue. But for the purpose of what we are explaining, we will take this out first. Let us continue the way we are going. So this now gives us a further, we know that 9 is 3 times 3 and we know that 8 is 2 times 2 times 2. So this already gives us the prime factorization of 72. Alright, so this is what we mean by splitting numbers within the root sign into their prime factors to make it easier for us to find the square root or to simplify it further. So because this is square roots, we now look at the numbers in pairs. Why are we looking at the numbers in pairs? Because we know that the whole idea of square roots is a number multiplying itself. So if we take 3 and 3 multiplying themselves, 2 and 2 multiplying themselves, what we will have left is just these 2 here. Now, once we've identified pairs like this, then we can take them out of the root sign finally. To take a pair like this out of the root sign, one of the pair will be sacrificed. This gives us 3 times 2. So this gives us 3 times 2 outside the root. Then what we have left in the root is just these 2 here. So this gives us 3 times 2, which is 6. So this gives us 6 root 2. So this is how prime factorization works. Now, some people may ask, why is it that we must change it to the prime numbers? Why must we use prime factors? Why can't we use just any factor that is not even prime? So far we know the square roots of such a number. For instance, this where we stopped here, 9. 9 is not a prime number, but we know the square root of 9. Why didn't we just pull it out and say 3? You can do that. It is not wrong. In fact, you are advised to do that if you know how to do that to make it faster for you. But the reason why I went ahead to talk about prime factors and prime factorization is because we know that once you get a prime factor inside these roots, there is no other simplification that can happen to that prime factor. For instance, look at what I did here. Once I got these 2, I know that root 2 cannot give me anything more. It will always end at root 2. I cannot simplify it further. But if I can expand this number into the prime factors, then I can group them in 2s and pull them out, and whatever is left here, I don't need to stress myself or bother my head about how to simplify them further. I just have to multiply what is left and put the answer, and I'm convinced that that multiplication I get will not give me anything simpler than that. That's the only reason why we are sticking with prime factors. It's not as if you use any other number, it is incorrect. You know what? Let us take an example that explains this thing that I'm talking about. So let's say we have root 360. Now, we don't know the prime factors of 360, but we do know that 360 is 36 times 10. For those that don't know, anything times 10, just put 0 behind it and it gives you that. That's how I knew that 360 is 36 times 10. Now, why did I use 36 times 10? Because I know the square root of 36. So it makes it easy for me, instead of trying to find the prime factors of each of them and writing a long list of 2s and 3s and 5s and so on. So once I do this, square root of 36 is already 6, so that pulls 36 off and gives me 6 root 10. We can go on to say this is the same thing as 6 root 10 is the same thing as 2 times 5. Now note that I did not say 10 is 7 plus 3. This will be absolutely wrong, because the whole idea of powers, roots, and everything we'll be talking about, this is a repetition. I keep on repeating it because this is a mistake students make all the time. The plus and minus are not involved in roots, anything calculation of roots, because roots belongs to the multiplication family. So we cannot convert 10 to 7 plus 3 or 2 plus 3 plus 5. That would be absolutely wrong. So we have to use factors, something that can multiply something to give you that 10, not something that can add something or something that can subtract something. Please pay careful attention to this. It is very, very important not to make this kind of mistake. So now let us get back to this. So this gives us 6 root 2 times 5. Now until I've seen these prime numbers that are forming as factors, I see these prime numbers as factors, I'm not satisfied. Now I've seen 2 times 5. I'm now sure that no further simplification can happen here, because 2 and 5 are prime numbers and none of them is repeating inside here that I can pull out and say I found the square root. So this is now the answer, 6 root 10. I can write it comfortably. But initially, because 10 is not one of those prime numbers, I cannot confidently leave it that way. I need to see 2, 3, 5, 7. So this is the reason why we always try to end up as prime numbers, just to be sure that we've simplified it to the simplest form. Now, earlier on, we said that we can say root 2 times root 5 because they are both multiplying themselves, that's multiplication family, and they are both roots. We can combine them and say root 2 times 5. It could also go the other way. If you see root 2 times 5, you could split it. So let's use another number entirely. So if we see root 4 times 5, we can split it to root 4 times root 5. This is mathematically correct. However, I keep on bringing this up any opportunity I have. If we had root 4 plus 5, it is not the same thing as root 4 plus 5. This is wrong because we are not dealing with roots. Once root is involved, it is not the addition family, it is multiplication family. So we cannot split it this way. Let's even see why it is wrong. Now look at this one. 4 plus 5 gives us 9. So this is root 9. And what is root 9? 3. Now let's look at this side. Root 4 is 2. Then this is root 5. So 2 plus root 5 is not the same thing as 3. So this is wrong. So please bear it in mind. The plus family does not go well with roots because roots belong to the multiplication family. So you cannot split something or a term or terms rather or expressions inside the root sign that have the plus family. You cannot split them into their individual components. You can only do that when they have multiplication and division. So far, for those of us following from lesson 1 of this series, you understand that what we are trying to say here is that the inside of a root is a mathematical community on its own that follows exactly the same principles that happen in mathematics on the outside of the root. It follows the same principle inside. So just like you can't combine plus and multiplication on the outside, even inside of a root, all the mathematical principles still apply. So that's what we are saying. Now, as you've observed, since we've been solving, we've been getting things like root 2, root 5, and so on. These roots, we can't solve them any further because when we solve them, even if you use a calculator, it gives you a decimal that goes on forever without having an end, and you won't even see a repeating pattern in those decimals. These roots are called surds. So surds are basically roots that cannot give you a rational number when you calculate them. So apart from root 2, root 5, we also have root 7, root 10, as we've seen in this case here, that 10 gave us no further simplification. So these are all surds. So in mathematics, surds are best left this way, root 2, root 5 or whatever. You don't use calculator to translate them into decimals, because the decimals will never give you anything recurring or anything ending. So surds are left this way. Most times surds occur as what we call mixed surds, like we saw when we did root 8. Root 8 is the same thing as root 2 times 2 times 2. So if you take the pairing, these two, and then one of the twos will sacrifice, the other two comes out. So this gives us 2 root 2. So a mixed surd is a surd that is multiplying a whole number. That's what we mean by a mixed surd. Okay, but you need to be very, very careful when you are talking about surds. Sometimes you see a root. This is why I explained before about prime factorization. Sometimes you see a root and you think this is a surd. It can't go any further. But you need to be sure. That's why you need to know your prime numbers. So if we had, for instance, root 2 plus root 8, you may conclude and say these two are unlike surds. They can't go any further, but they actually can. Root 2 we know is a surd, but root 8 is not the way we think it is. If we find the prime factors of 8, it gives us 2 times 2 times 2. And if we take the pairing, these two, one off and one goes out. Then this now gives us root 2 here plus 2 root 2. That is this 2 that is left and the 2 that went out. So now this now becomes a like surd, because this is 1 here, this is 2 here. So this is 1 root 2 plus 2 root 2. That gives us 3 root 2, just like variables. So what you need to take away from this particular explanation is that before you conclude that two roots that are adding themselves are unlike, you need to simplify the roots until you get to the prime factors that can no longer go before you say they are unlike or not. It is very, very bad practice in mathematics to leave surds below, that is in the denominator. Anytime you have surds below, always move them to the numerator. Don't leave surds as your denominator as the final answer. That is very, very bad in mathematics. So how do you do that? It is through a process we call rationalization of the denominator. Now let's look at this example to understand it better. If we had 1 over root 2, you can't leave your answer this way. So what do? You multiply by root 2 over root 2. So you are multiplying by the denominator, that root 2. The whole idea is you want to clear this root 2 and pull it above. Now some people will be saying, why are we multiplying by something that wasn't in the question? We are literally not multiplying by anything except 1, because if this cancels this, it still gives you 1. So what we are basically doing nothing, because anything multiplied by 1 is still that same thing. So what we are doing is that we are trying to use a technique, an idea, to get rid of the root 2. That's why we are doing it that way. So anytime you have surds in the denominator, multiply by that surd or a combination of what it is that is in that denominator up and down like this. So let's get back to this. So if we wanted to now rationalize, as we've done now, to complete simplification, you cannot cancel these two out, because that's the whole idea of this. So what you do, you multiply this straight through. That gives you root 2. Then root 2 times root 2 gives you root 4, and root 4 is 2. So this gives you the answer, root 2 over 2. When a root multiplies itself, or the square of a root is that number without the root and the square. So that's why root 2 times root 2 is 2. We already know how this works. I don't need to start explaining it. If we had something complicated like 1 over root 2 plus 1, in such a case, we will multiply it by what we call the conjugates. That is, conjugate just means changing this plus to minus. That is changing it to its sibling. So that will give us root 2 minus 1. We are multiplying by root 2 minus 1 over root 2 minus 1. Now, if we simplify this further, we have to talk about expansion of brackets and all, which is not what this lesson is all about. I'm just trying to show you that surds cannot remain in the denominator. So in a case where it's just a single surd like this, like this, you multiply it by that surd. But if you have a surd that is like an expression like this, you change it, the sign, to its conjugate, that is the sibling. Change the plus to minus or minus to plus in the multiplication so that you get an appropriate answer. We will do this in the other algebra series. Now, some people may ask questions. Why are we just talking about square roots when we are talking about surds? Does it mean that surds only involve square roots? No. Surds don't only involve square roots. Surds involve anything, any root at all. Fifth root, fourth root, cube root, and so on. The reason why we're using square root is because, like we said, this second root or square root is the most popular root. So the surds you will likely encounter throughout your mathematical journey in this high school or secondary school is surds as square roots. You are very, very unlikely to see surds as cube roots, but surds as cube roots will also exist, especially for mathematicians and those on a higher level of learning. But if you apply the same logic, you will know that if we are looking at cube root of 8, for instance, in this case, cube root of 8 will no longer give you a surd because 8 will now be a perfect cube. So cube root of 8 is 2 because 2 times 2 times 2 is 8. So that's the difference between the surds we see in square roots and the surd we see in other roots. So a number may be a surd, or a root may be a surd when you are looking at it as a square root, but may not be a surd when you are looking at it as another root, cube root, and so on. It's just important for me to mention so that the knowledge will be complete, but it is very, very unlikely that you will encounter surds other than square roots. So now, let us take a few examples of the things we've discussed so far on roots and surds. Now, look at this first one, 2 root 3 times 3 root 2. So we multiply the whole numbers first, which is 2 and 3. It gives us 6. Then, from what we've discussed, we can combine these two roots to be 3 times 2 inside it because they meet the requirement. They are multiplying themselves and they both have the square root. So this gives us 6 root 6. Very easy. And because 3 and 2 are both prime factors, we were definitely confident that root 6 will be a surd. There is no other simplification that can go on in that root 6. So this will be the answer. Now look at this particular question. What we will do is to split the numbers in the roots to their prime factors, or at least start with what we remember. So this gives us 3 roots 4 times 3 plus roots 9 times 3. Now we know the square roots of 4 and 9. So if we get it out, this becomes 3 times 2 root 3, that is the root 3 remains, plus if 9 goes out here, it becomes 3, so 3 root 3. So 3 times 2 is 6, so this is 6 root 3 plus 3 root 3. Now we see that we are talking about like surds now, root 3 and root 3. Because they are like surds, we add them as if we are adding variables. So that gives us 6 plus 3, 9. So this is 9 root 3. And that becomes the final answer. Now let's take this as the final example for this section. So 5 over 2 root 3. Now we can't simplify this any further in the sense that if we divide 5 by 2, it gives us a decimal, and that's not what we want. We are not doing that yet. So we are going to rationalize the denominator. So to do that, we will just multiply by 2 root 3 over 2 root 3. So 5 times 2 root 3 gives us 10 root 3 over, now 2 times 2 is 4, root 3 times root 3 is 3. Now if we cancel out, remember we are not cancelling out what is inside the roots. What we are cancelling out is the numbers outside the roots. So 4 divided by 2, 2, 10 divided by 2, 5. So the final answer becomes 5 root 3 over 2 times 3 is 6, 6. Finally, before we wrap up our recap or our refresher, you need to know, I don't want to use the word memorize, but you need to know the squares of numbers 1 to 15 or even 20, because it helps you to solve things very, very fast. And you don't need to memorize it. The more you solve, the more you get used to them. It will come naturally. So as you solve, you begin to see a lot of squares and you get used to them, squares and square roots. In the same way, you need to memorize the cubes of numbers 1 to 10 at least. For the same reason, again, you don't need to sit down to start memorizing it. As you solve more and more problems, you begin to see the cubes, the cube roots, and so on, and you get used to them. Now, with this recap, let us now go to powers in algebra proper. Now, in algebra, is there any difference? Absolutely not. There is no difference between the powers you see in numbers and the powers you see in letters or variables or algebra. The only thing I need to mention is that if you had 2 times x, maybe raised to power 2, the answer is 2x raised to power 2 or 2x squared. Because just like we discussed in the previous lesson, you can remove the multiplication sign when you have a variable multiplying a number, so it gives you 2x squared. But you cannot have 2 times 3 raised to power 2 to give you 3 squared. No, this is wrong, because the two numbers can be joined together. So you cannot represent it like this, 3 raised to power 2 or 23 squared. No, it will be wrong. So it's only letters that you can do, you can apply this to, because you don't know what those letters are. Alright, so this is the key difference between algebra and when the numbers are known. Now let us go to arguably the most important parts of this lesson, the laws of exponents or the laws of indices. Now, what are these laws or rules of exponents or indices? These are simply those rules that help us simplify powers more easily. There are 6, or some people say 7 of them. You will see why I said 6 or 7. There's one of them that is usually not considered one of the rules, but it's still very important to know. So we'll go through them one by one, and you'll see that they are very, very easy. Once you master them, it will be easy for you to manipulate powers anywhere you see it. So the first rule of exponents is what we call multiplication with same base. This means that if we had x raised to power m, for instance, multiplying x raised to power n, note that this x, m, and n are just representatives of what we will see. It doesn't have to be m and x or n exactly. This is just to tell you that anytime you get a format like this, this is what you do. So if you have x raised to power m times x raised to power n, the answer is you put the base, that is provided these two bases are the same, you put that same base x and then raise it to the power of the addition of the two powers, m plus n. So the first law of indices that we are looking at, multiplication with same base, is telling us that if we had x raised to power m multiplying x raised to power n, the answer is that same x but raised to power of m plus n. Now let's take an example to make it clearer. If we had 3x raised to power 4 times 5x raised to power 3, then we are saying that the answer, when we multiply the numbers like we did in the previous lesson, it gives us 15. Then what we are left with is x raised to power 4 times x raised to power 3. So what this law is saying is that based on this setting, the answer here will be 15 times x raised to power 4 plus 3. Why? Because this x and this x are the same. They have the same base. That is, this x raised to power 4 and x raised to power 3 have the same base. So because they have the same base and they are multiplying themselves, you can add their powers and retain the base. So the final answer will be 15x raised to power 7. Now, be very, very careful here. The laws of indices don't have anything to do with addition. The initial expression must be a multiplication. It is not x raised to power m plus x raised to power n. No. In this case, the laws of indices or exponents will not apply. It is only when the two powers or the two terms that have powers are multiplying themselves, not when they are adding themselves. So when they are multiplying themselves, then you add the powers. We now go to the second law. So the second law of indices that we will look at is what we call division with same base. So like we did in the first law, if we had x raised to power m, this time around dividing x raised to power n, the answer here is x raised to power m minus n. So this is very similar to the first law. The difference here is that one of the terms is dividing the other, unlike the first law where one is multiplying the other. So in this case, when it is division, then the two powers will subtract themselves. Again, this has nothing to do with plus and minus. It is not x raised to power m minus x raised to power n is equal to x raised to power m minus n. No, it is x raised to power m divided by x raised to power n now gives us x raised to power m minus n. This is very, very important to note because this is one of the common mistakes students make. Please pay careful attention here. So let's take an example. Now look at this example. 12x raised to power 9 divided by 4x raised to power 5. In this case, reference to lesson 4 again, we divide the numbers first. 12 divided by 4 gives us 3. Then we have x raised to power 9 divided by x raised to power 5. Now if we want to apply the law, it is telling us that this will be x raised to power 9 minus 5. So the answer now becomes 3x raised to power 4. Again, please pay careful attention. It is not when the two bases are subtracting themselves. It is when the two bases are dividing themselves. Please pay careful attention here. In fact, let me just slot this in for those who have been following from the first lesson. If we had a situation where we had x raised to power m minus x raised to power n, you cannot solve this any further based on what we've learned so far. These two terms are unlike terms because they have different powers, so you cannot even subtract them. The laws of indices don't apply to subtraction or addition of the two terms. They only apply to multiplication and division. In fact, the entire 6 or 7 laws have nothing to do with addition and subtraction. They only have to do with multiplication and division. The rules of exponents or the laws of indices are entirely for the multiplication family, not for the addition and subtraction family. We now go to the third law. The third law of indices is what we call power of a power. In this case, we are saying that if we had x raised to power m and all raised to power n, then the answer is x raised to power m times n. This is pretty straightforward. If we had two powers, that is a power of a power, then you just multiply the two powers and it gives you the answer. So let's take an example of this. If we had x raised to power 2 all raised to power 5, then the answer is simply x raised to power 2 times 5, which is x raised to power 10. This law is very, very easy. We now go to the fourth law, which we call power of a product. Now let us switch it up a bit. Let us use another letter to make people know that it doesn't have to always be x, x, x. So for this power of a product, we are saying if we had a, b, all raised to power n, then it is the same thing as a raised to power n, b raised to power n. So power of a product is simply saying if the two variables that are multiplying themselves and raised to a particular power, then that power belongs to each of those variables individually. So let's take an example here. If we had 2x all raised to power 3, then the answer is 2 raised to power 3 x raised to power 3. That is what this fourth law is saying. If we simplify it further, 2 raised to power 3 or 2 cubed is 8. So it will be 8x raised to power 3. So another very, very easy law. Now we go to the fifth law. The fifth law of indices is what we call power of a quotient. It's very, very similar to the fourth law. It's saying that if we had a divided by b all raised to power n, then this is the same thing as a raised to power n over b raised to power n. It is very similar to what we just did, that if the power of a combination of those two variables dividing themselves, then that power belongs to each of the variables individually. So let's take an example here. 3x squared over 4y all squared. It means that the answer to this is 3 squared, then x squared bracket squared again, that is the squared goes for x squared as well, over 4 squared y squared. So if you simplify this further, 3 squared is 9, x squared squared is based on one of the previous laws we've already looked at, is already x raised to power 4, then over 4 squared is 16 y squared. So that's the answer for this. Now note that for this particular law that has to do with division, and even the second law, any of the laws that have to do with division, the denominator or the number that is dividing must not be 0. because we know that anything divided by 0 is undefined. So provided that number that is the denominator is not 0, that is in this case b must not be equal to 0, then the law stands. But if b is equal to 0, then the law will not stand because anything divided by 0 is undefined. Now we move to the sixth law of indices or rules of exponents. This is what we will call negative exponents. This is telling us that if we add x raised to power minus n, it is the same thing as 1 over x raised to power n. And if we add 1 over x raised to power minus n, it is the same thing as x raised to power n. So what we are saying in this law, which is negative exponents, is if you want to remove the negative sign of the exponent or the index or the power, all you need to do is push the entire base down or up depending on where it was before. That is, push it to the opposite position. So if it was the numerator, you put it in the denominator. If it was the denominator, put it in the numerator. In other words, if a base moves from numerator to denominator, its power becomes negative. If a base moves from the denominator to the numerator, its power also becomes negative. In other words, the operator or the sign of a power changes to the sibling once it moves from the numerator position to the denominator position, or vice versa, which is from the denominator position to the numerator position. So if it had minus before, if it changes position, then it becomes plus. And if it had plus before and it changes position, then it becomes minus. This law is very, very easy to remember. So let's take an example. If we had x raised to power minus 3, then we are saying that this is the same thing as, because x is a whole number, is a numerator by default, then if we move the x to a denominator by writing 1 over x, then we should change the power to 3 instead of minus 3. So that's what this law is saying. So let's take another example. If we had 5 over x raised to power minus 2, we are saying that we can rewrite this as 5x squared, or 5x raised to power 2, by moving the x raised to power minus 2 from the denominator to the numerator, and it will now change the sign of that power or index from minus 2 to 2. Now the seventh law or rule of exponents, which some people don't agree that it should be a law, is what we call zero exponent. This is very easy. I think most people know this. It just means that anything raised to power 0 is 1. So x raised to power 0 is 1, 5 raised to power 0 is 1, 2 raised to power 0 is 1, anything raised to power 0 is 1, provided that x is not equal to 0. Because 0 cannot be raised to power 0 and it cannot be 1. So here are the laws of indices displayed on the screen. You don't have to sit to start memorizing them. There are very, very easy ways to get used to them. One of those ways is by solving. The more you solve, the more you get used to them. They become second nature. A quick tip to master these things. First of all, you see this first law here? This first law and this second law. All you need to remember is if the bases are the same, that is a, x, y, 2, 3, 3, whatever it is, and they are multiplying themselves, just add the powers. That's all. For the second law, same scenario, but they are now dividing themselves instead of multiplication. You subtract the powers. Easy for you to remember. Multiplication looks like addition, but in a kind of upside down way. So when you see multiplication, you add the powers. If you see division, which looks like subtraction anyway, if not for the 2 dots there, then you subtract the powers. That's all. So let's take notes. Now that we've looked at all these laws, let us now take real examples that combine all the laws. So let's start gradually. So for this one, x raised to power 4 times x raised to power 3. So this is a straightforward first law. So that gives us x raised to power 4 plus 3, because the bases are the same and they are multiplying themselves. So this gives us a final answer of x raised to power 7. For this second one, 4x raised to power 3 times 3x raised to power 5. We will collect like terms in the multiplication family way, not the collect like terms of addition and subtraction we did in lesson 2. We are doing that because the operator here, the only operator here, is multiplication. So we are allowed to do that. So to collect the like terms gives us 4 times 3. We've moved the numbers together. Then that gives us times x raised to the power 3 times x raised to the power 5. So we collected and split them. Okay, so 4 times 3 gives us 12 times x raised to the power 3 times x raised to the power 5 is the same thing as x raised to the power 3 plus 5, based on the first law that we talked about, multiplication with the same base. So this will give us a final answer of 12x raised to the power 8. For this third example, 6x squared times 3x raised to the power 3 divided by 2x, we will do the same thing we did in the previous example, but you need to bear in mind that before we collect the like terms, like we said in the previous lessons, every operator to the left of a term belongs to the entire term. It doesn't belong to just one member of that term. So it means that this divided by 2x, the divided by belongs to both 2 and x. So when we are moving 2 to the number side, it will carry divided by. And when we are moving x as well to the x side, it will also carry divided by. It won't carry multiplication. Another way to look at it is, if we convert this divided by 2x to multiplication, it becomes times 1 over 2x. It doesn't become times 1 over 2 then times x. No, it becomes times 1 over 2x. So that tells you that the divided by belongs to 2 and then belongs to x individually. So that's exactly what we are going to do now. Let us not use this method of pulling it as the denominator because we want to apply the laws. So let us do the initial method. So I take this off. So what we have now is, if we are going to group the terms, let's move the numbers first. So if we collect the numbers first, so we are collecting this, this, and this. And we are collecting them with the operators, of course. So this gives us 6 times 3 divided by 2. Then for the letters, that is the x, we are collecting this, this, and this. Remember, divided by will go with the x. So it gives us x raised to the power 2 times x raised to the power 3 divided by x. Now, because we want to cancel out the numbers, we will change this divided by 2 to multiplication. So it gives us 6 times 3 times 1 over 2. Then for the x, if we apply the laws number 1 and 2, it gives us x raised to the power 2 plus 3, because this x raised to the power 2 and 3 are multiplying themselves. But because this is divided by x and this x has 1 here, anytime you don't see any power, it is 1. So because it's divided by, it will now be minus 1 based on the second law. So if we cancel this out, 2 we cancel 2, 2 we cancel 6 to give us 3. Then the final answer will be 3 times 3, which is 9. Then x, 2 plus 3 is 5. 5 minus 1 is 4. So this is x raised to the power 4. So the final answer is 9x raised to the power 4. Now, for this question, 3a squared b all raised to the power 3. First of all, don't make the mistake some students make. Because you are seeing this raised to the power 3 close to b, doesn't mean it belongs to just b. As you can see, the 3a squared b is in a bracket before the raised to the power 3. So it tells you that that power of 3 belongs to all of them in that bracket. So what does it mean? It means that this question is a question where we have to apply power of a product. That is, that raised to the power of 3 we have to be the power of all of them individually before we can solve it. So to do that, we will now write 3 raised to the power 3, a squared raised to the power 3. As you can see, I put the a squared in bracket before I put the 3 to show that that raised to the power 3 is for the a squared alone. Then b raised to the power 3. So if we simplify it further, it gives us 3 raised to the power 3 is 9. Now, a squared raised to the power 3 is now another law, which is power of a power. And that law says we should multiply the two powers. If we have a power on top of a power like this, we should multiply the two powers. So that means this is giving us a raised to the power 2 times 3, then b raised to the power 3. If we solve it further, it now gives us 9a raised to the power 6, b raised to the power 3, and that becomes the final answer. You see how easy it is once you know how to identify the laws and how to use them. Now look at this question. This one is definitely more difficult than the previous ones, and it says simplify fully and write with positive indices, which means it doesn't want any negative index in the answer. So the first thing we are going to do is, for this one on the left, we are going to apply power of a product, 3x squared y raised to power minus 1 all raised to power 2. We are going to use the power of a product for this. First, let's do that first. So that gives us 3 raised to power 2. By the way, if you forgot, in power of a product, the law of power of a product is saying that raised to power 2 goes to all of them, becomes the power of all of them in the bracket. So this is 3 raised to power 2, x squared, we put it in bracket, raised to power 2, y raised to power minus 1, we put it in bracket, raised to power 2. So that sorts out that left side. On this right side, divided by 9x raised to power minus 1 y squared. Now, as you can see, everything is in bracket to show you that the divided by belongs to all of them, not just 9. Please avoid that mistake. So it means that we can rewrite this as divided by 9 divided by x raised to power minus 1 divided by y squared. I didn't change anything. I just made sure that I assigned the divided by to all of them individually. Now, the next thing we will do is to collect like terms in the multiplication family way, which we've been doing since the previous lesson. When we do that, we will get 3 raised to power 2 divided by 9, because those are numbers. Then the next, we want to collect the x now. Let's put this in bracket first. Then x raised to power 2 raised to power 2 divided by x raised to power minus 1. What we are taking is this and this. Then we are now taking the y, this and this, as the next bracket. Y raised to power minus 1 raised to power 2 divided by y raised to power 2. What we just did was we separated the numbers from the x and the y so that it will be easy for us to apply the laws. Now let's continue solving. 3 squared is 9. 9 divided by 9 is 1. So this is sorted. Now for this x raised to power 2 raised to power 2, we are going to apply power of a power here. So that gives us x raised to power 4, that is 2 times 2, 4, divided by x raised to power minus 1. Now for the y, same thing, power of a power, y raised to power minus 1 times 2 will give us y raised to power minus 2. If you don't know how to multiply negative numbers, watch the previous lesson. We covered everything about multiplication, division of negative numbers. So then divided by y raised to power 2. Now, this is pretty straightforward. We are now going to apply that second law, which is division with the same base, because we know that this base and this base are the same and they are dividing themselves. This base and this base are the same and they are dividing themselves. So this will now give us, we are ignoring this one because there is no point. So this will now give us x raised to power 4 minus 1. Minus 1 is because this is minus 1. You cannot throw away this minus simply because you are converting division to minus. That will be mathematically wrong. Then for the y, we have y raised to power minus 2, which is the division becomes minus, then the 2 is here. So simplifying this further gives us x raised to power 4 minus 1 is the same thing as 4 plus 1. If you don't know how to add and subtract negative numbers, check the previous lesson, lesson 3. We covered all that, all the basics. Then y raised to power minus 2 is minus 4. So this gives us x raised to power 5, y raised to power minus 4. But the question says, as you see here, simplify fully and write with positive indices, which means the question doesn't want this minus here. And to remove this minus here, we now have to apply one of the laws, which is the law of negative exponents, that tells us that if we want to change this y raised to power minus 4 to y raised to power 4, all we need to do is move the entire thing downwards since it is upwards now. This will now become x raised to power 5 over y raised to power 4. This is the same thing as over 1 anyway. So when we move this down, then the minus in the 4 will become plus. And that's why we have x raised to power 5 over y raised to power 4. And that becomes the final answer. Now look at this one, exactly the same thing as the previous one, but this is just to reinforce what we've learned. So this gives us 20 x raised to power 6 y raised to power minus 3 divided by 5 divided by x raised to power 2 divided by y, just like we did in the last one. Now we can collect like terms in the multiplication family way, and so it becomes 20 divided by 5 x raised to power 6 divided by x raised to power 2. Remember what we are doing, this and this, x raised to power 6 here and x raised to power 2 here. Then for the y raised to power minus 3, which is this, divided by y, which is this. So 20 divided by 5 is 4. X raised to power 6 divided by x raised to power 2, based on the second law, division with same base, that gives us x raised to power 6 minus 2. Then for y raised to power minus 3, this y here has 1. So y raised to power minus 3 divided by y raised to power 1. That is y raised to power minus 3 minus 1. So this gives us 4x raised to power 6 minus 2 is 4. So x raised to power 4. Then y minus 3 minus 1 is minus 4. So that gives us y raised to power minus 4. If we are going to rewrite this to remove the negative index, which is what the question wants, the question doesn't want negative index, only positive. So that will now give us 4x raised to power 4, because these two are okay, they don't have any negative index. The problem is this y. Once we bring it down, it becomes y raised to power 4. And that now becomes the final answer. Now look at this one, definitely more difficult than all the ones we've done before. It says simplify fully, rationalizing the denominator where necessary, and also express with positive indices only. So just like we've been doing since, this divided by belongs to everything in the bracket. So we are going to assign it to all the terms and even members of the terms one by one. Let us do that now. So that gives us 3x squared roots. As you can see, the bracket tells you that everything inside belongs into the roots, not just 12. So root 12x squared y divided by 6 divided by x divided by root 3y. Next, we are going to collect like terms in the multiplication family way, like we've been doing. But remember, the inner part of a root is sacred, so we can't touch it except we are joining it with another root, in which case we can do that since this is the multiplication family. All the operators are siblings. So what we are now doing is we are going to split this 3 and this one and split all of them like that with their operators. And then we collect them. So numbers first. 3 divided by 6. Then let's look at the x. So we've accounted for this 3 and this 6. So let's look at the x next. Let's put a bracket here. So x will give us x squared here. Then we take this divided by x. Then what is left? The roots. So what is that root? Root 12x squared y divided by root 3y. Now, from what we've learnt, we see that we can combine these two roots because they meet the requirements for combining. First of all, both of them are roots. And secondly, they are dividing themselves, which means division is part of the multiplication family. So they meet that requirement. So that's what we are going to do next. So that now gives us 3 divided by 6 is 3 over 6. X squared, let's still leave it this way. X squared divided by x. Then root 12x squared y over 3y. Now before we move on with the roots, we now have to cancel out to see if it can help us simplify the roots further, because we don't like seeing roots in our answers. So while we cancel y, remember this is from lesson 4, the previous lesson. That's why I said you need to master the previous lesson, which is multiplication and division basics, before you start talking about powers and roots. 3 will go here, 1. 3 will go into 12 to give you 4. So what we are now left with is 3 over 6 x squared divided by x root 4x squared. Now let's look at this 4x squared and see the ways we can simplify it. We are very lucky that this question is pretty straightforward. Now if you have root 4x squared, if we wanted to use the first method, we can say 4 is 2 times 2. Then x squared is x times x. And based on what we talked about in the pairing, this is a pair, this is a pair. And if we have pairs like this in square roots, then one of them will be sacrificed to get the other one out. This one will be sacrificed to get the other one out. So the root disappears completely in this particular question, and that will now give us 2x as the answer. Or we could just say root 4x squared is the same thing as root 4 times root x squared, and we know that root 4 is 2. X squared, root x squared is x, because for you to square x and find the root, it still gives you x. We've been saying this since. Or if you wanted to apply one of the laws, we can say x squared raised to power 1 over 2. That is if we change the root sign to raised to power half. And if we now use power of a power here, it will now give us 2 times x raised to power 2 times 1 over 2. 2 will cancel 2 to give you 1. So that still gives us x raised to power 1. So the answer will still be 2x. So this question is one of those straightforward questions that helps us remove the roots easily. So we are coming back now here. So we already have the answer of this as 2x. So that now gives us 3 over 6 x squared divided by x times 2x. We will now have 3 times 2 over 6. That's if we move this 2 into this number region. Then x squared divided by x times x. That's if we move this x into this region here. So that now gives us 3 here 1, 3 here 2. 2 we cancel 2, so no number left except 1. Then for the x, if we apply the law, it gives us x raised to power 2 is dividing x, so that is 2 minus 1. Then is multiplying x, that is plus 1. So the final answer will be 2 minus 1 is 1, then 1 plus 1 is 2. So that gives us x squared as the final answer. You see how your knowledge of all these laws and other things we've talked about helps you to solve the problem. That is the whole idea of math in full. Look at the entire mathematics in full. Don't look at it in fractions. Your entire knowledge is what makes you good in mathematics. Now, this is the most difficult so far, and it's going to be our last challenge before we will drop the try exercise. Now, for this one, to approach it, because it is quite complicated, especially having a lot of brackets and things multiplying themselves inside brackets, it will be very difficult to use the other pattern we've used before. So the first thing we will do is to write this in the numerator denominator pattern first, so that we can understand what we are solving. So let's do that first. So what I did was to rewrite the equation so that the orientation looks more familiar to all of us. So just in case you are wondering how what I wrote is the same as what you can see here. As you can see, we already know 2a raised to power minus 1 b squared all raised to power 3 is the same thing I wrote. Then multiplied by root 18a raised to power 3b. As you can see, the 18a raised to power 3b is in brackets within the root shade. So that tells you that the root covers all of them. And now because I'm writing it with freehand, I removed the bracket and I extended the root to cover them all. Then I removed the multiplication sign because I already told you that if something is multiplying a root, you don't need to put the multiplication sign. So that's why I removed it. Then coming below over, now there's a big bracket covering everything that is below in the original question because the division sign is slanty. So they need you to know that everything here is supposed to be below. That's why this big bracket is here. So I must move everything below and remove the big brackets because it's no longer useful. So that's basically what I did. The 2ab raised to power 3 that is in the root here, I also removed the bracket because I extended this root shade to cover the 2ab raised to power 3. Then of course the 3a squared b raised to power minus 1 all squared, I left it the way it is. So this is the question. Now it's easier for us to know what we are solving and how to approach it. Now when you see this kind of question, you first of all check, is there any operator that is not from the multiplication family? We don't see any operator that is not from the multiplication family. There is no plus, there is no minus. So you are happy, at least it's not going to be a complicated solving because we've not done that yet in this series. Now after confirming that you are dealing with the multiplication family, the next thing to do for this kind of question is to find a way to get rid of the root sign. If you can, as much as possible, try to get rid of it. Even if you can't, try and solve anything within the roots to see if it will help you eliminate the root sign, because we don't want roots in our answer. as much as possible. So that's what we will do. And because we know this is the multiplication family, we are permitted to rearrange and move things the way we like, except the inner part of the root, of course, which is sacred. So let us move all the roots away from the main equation and try to solve the roots and see what we will get out of it. So what I'm basically doing is I'm going to split this equation here into half and write this part and this part separately so that we can solve this part and see what it gives us. So as you can see, we now have 2a raised to power minus 1b squared all raised to power 3 over 3a squared b raised to power minus 1 all squared, then times root 18a raised to power 3b over 2a b raised to power 3. So what I did was not just to split it, I combined both roots. Why? Because both of them meet the criteria for combination of roots like we explained before. They are both bearing the badge of the multiplication family because they are dividing themselves, and they are both inside the root signs themselves. So that's why we could combine them. So now let's start solving based on the laws. So for this upper part, we have this cube here applies to everything in the bracket. So based on the law of power of a product, so the 3 belongs to all of them. So this gives us 2 raised to power 3, a raised to power minus 1 times 3 is minus 3, b raised to power 2 times 3 is 6, over, same thing here, power of a product. So it gives us 3 raised to power 2, a raised to power 2 times 2, which is 4, b raised to power minus 1 times 2, which is minus 2. Then for the roots, since we've created the root community, we now have to cancel out 2 into 2, 1, 2 into 18, 9. Now within that root, let us convert the denominator and numerator pattern to the division pattern so that we can see clearly and apply the laws. So this gives us multiplied by the square root of 9, a raised to power 3 divided by a, b divided by b raised to power 3. Now let's do the same thing on the other side. So this still remains 2 raised to power 3 over 3 raised to power 2. Then a raised to power minus 3, b raised to power 6 divided by b raised to power minus 2. We know that root 9 is 3. So let's just write it and pull it out. So this becomes times 3 roots. A raised to power 3 divided by a is a raised to power 3 minus 1 because there is a 1 here. Same thing, there is a 1 on the b here. So that gives us b raised to power 1 minus 3 because it's also division and they are the same base. Now I'm still going to leave the powers on the numbers so that I can show you that the laws of indices or exponents also apply to numbers. So let's leave this way. So we still write it the way it is. 2 raised to power 3 over 3 raised to power 2. Then this is a raised to power minus 3 divided by a raised to power 4. So that's a raised to power minus 3 minus 4 based on the law of division with the same base. Then b raised to power 6 minus 2, same law. Then times 3 roots. A raised to power 3 minus 1 is a raised to power 2. B raised to power 1 minus 3 is b raised to power minus 2. So simplifying further still gives us 2 raised to power 3 over 3 raised to power 2. A raised to power minus 3 minus 4. That is a raised to power minus 7. B raised to power 6 minus 2. Minus times minus is plus. So that is 6 plus 2. So that gives us 8. B raised to power 8 times 3 roots a squared. If we move the b raised to power minus 2 down, it becomes b squared. The next thing we will do now is to remove the roots. And to remove these roots, we know that if anything is squaring itself and still in a root sign, they can cancel out. So this a can come out of the root by cancelling its square with the root, and the b also come out of the root by cancelling its square with the root. So the root is gone. So we will now have 2 raised to power 3 over 3 squared, a raised to power minus 7, b raised to power 8 times 3a over b. So now let's collect like terms in the multiplication family way. So we are moving this 3 to meet this 3 and this a to meet this a here. So that gives us 2 raised to power 3 divided by 3 raised to power 2, which is this 3 raised to power 2 here, multiplied by 3, which is this 3 here, multiplied by a raised to power minus 7, which is this one, multiplied by a, which is this one, multiplied by b raised to power 8 divided by b, which is this b down. If you notice, I made sure that all the ones below I used divided by, and all the ones that were above I used multiplication, so I don't make any errors. No errors here. So we are rounding off now, completing with the laws. Now I'm going to put brackets so that we don't get confused. We put a bracket here, b raised to power 8 divided by b to distinguish b, a raised to power 7 divided by a to distinguish a. Now for this 3, I want to put a bracket, but I have to take the divided by here to show that this divided by belongs to this 3, so that I don't accidentally multiply it. So now we want to apply the laws again. So this gives us 2 raised to power 3. Then in this bracket, I'm going to rewrite this as 3 divided by 3 raised to power 2, just so that the division sign can come forward and it will look like something familiar with the laws. Then multiplied by a raised to power minus 7 plus 1, because this is the same base. Multiplication is plus when you're adding the powers here. Then times b raised to power 8 minus 1, because this is same base and they are dividing. I'm taking my time to do it this way because we are still learning. So, but over time we won't have to start writing the steps like this. So this gives us 2 raised to power 3, which we can change to 8 now. Here still becomes 3 raised to power 1 divided by 3 raised to power 2. Now this is just to show you that the laws of indices also apply to numbers, not just letters. So these are the same base, 3 and 3, and they are dividing themselves. So this gives us 3 raised to power 1 minus 2 times a raised to power minus 7 plus 1 is minus 6. Then b raised to power 8 minus 1 is 7. So this b raised to power 7. So this gives us 8 times 3 raised to power 1 minus 2. 1 minus 2 is minus 1. So that is 3 raised to power minus 1. A raised to power minus 6. B raised to power 7. Now if we want to take away the negative indices, we move all the ones with negative below. So this now finally gives us 8 b raised to power 7 over 3 a raised to power 6. We moved these two below so that the 3 raised to power minus 1 becomes 3 raised to power 1 and the a raised to power minus 6 becomes a raised to power 6. So this becomes the final answer. As easy as that. Here are the try exercises for you to test yourself and solidify your skills. As usual, try them first before the solution comes out. And we've improved the try exercises in levels so that so many more people can participate, because some people complain that some levels are more than what they can do. So this is why we have the try exercises in levels. If you do the first one, you feel more confident, you can do the other ones as the case may be. Check the description of this video for the guide to the levels and what the levels are all about. The color codes also will give you an idea of what the levels are all about. Check our website mathinfo.com for so many more exercises like this to be sure you've mastered everything you need to know about powers. The next lesson is going to be on removing brackets, which is one skill you must know if you want to be very good at algebra, at mathematics generally. We are already halfway through the series, and hopefully once we finish, you'll be a master of basic algebra. So this is a wrap on lesson 5 of basic algebra in full. Keep studying, and as you do, remember, in mathematics, it's all connected.